Here are some final thoughts regarding the other distributions that have been introduced concerning lifetimes. This is a chart, and I know this is going to be very hard to read. It is in the book also. And this chart shows how all of these lifetime distributions relate to one another. You can see that the exponential distribution right here is kind of a hub in terms of the number of distributions that it is related to. On the first line here within the exponential distribution is the name of the distribution. Then the second line contains its parameter, and then finally the third line contains its support. There are solid lines here, and there are a couple of dashed lines as well. The solid lines are going to denote special cases. So for example, if you look at the Weibull distribution, which is right here, and you consider the shape parameter being equal to 1, then that collapses from the Weibull to the exponential, and that's an example of a special case. On the other hand, if you take, for example, the exponential distribution and you transform an exponential random variable t by dividing it by lambda and taking a square root, that leads you along this path and the little half arrow that you see there to the Rayleigh distribution. And there is also another path going in the opposite direction from the Rayleigh to the exponential distribution. But you can see just about all of the distributions that we have encountered so far in this chapter show up in this particular graph. Another example up top here is the gamma distribution. That gets used quite a bit. Here is the log normal, which I told you is used quite often. And you will also find the log logistic distribution down here. But all these arrows show you special cases and transformations. Now, on occasion, you are going to see dashed arrows, like the one that heads from the gamma to the normal distribution, or this one right here, which goes from the Muth to the exponential distribution. Those will show up when you have what are known as limiting distributions. So for each of the survival distributions in that chart, you have the name first of all on the first line, the parameters second on the second line, and then you have the support on the third line. Again, relationships between these distributions, solid arrows denote special cases and transformations, dashed arrows denote limiting distributions. This website down below here is a superset of this particular figure that you saw on the previous page, and it contains more distributions, not only those with non-negative support, but all distributions, some like the normal, which have support from negative infinity to infinity. The UDR that you see right here and right here, that stands for univariate distribution relationships, and this was put together by a number of the computational operations research students at William and Mary. The next page contains distribution classes. So if we draw a line right here where the first break is, another line here on the second break, and here the third break, these distributions up top here, these are one parameter distributions, and this second group, which is right here, these are two parameter distributions. These right here are three parameter distributions, and finally down at the bottom there are n parameter distributions. Across the top, these tell you if they can be in the IFR class, the DFR class, whether or not they can take a bathtub-shaped hazard function or an upside-down bathtub-shaped hazard function. As you can see, the exponential distribution is the only distribution with a constant failure rate, or constant hazard function, I should say. And that says you have a yes in both boxes here for all lambda. So it is kind of the borderline between the IFR and the DFR cases. Couple things to notice. First of all, if you have a situation where you believe that your data values are well fitted to a bathtub-shaped distribution, you don't get a lot of options. You can see all these no's here. There is a yes for the exponential power distribution when its parameter kappa is less than 1, and there is also a yes for the IDB distribution, if you remember that one, increasing, decreasing bathtub, and it assumes the bathtub shape when the parameter delta lies between 0 and gamma kappa. So again, not many options in the case of bathtub-shaped lifetimes, and the same is true for the upside-down bathtub-shaped hazard functions. You only have 3 choices, and those 3 choices are the log normal distribution, the log logistic distribution, and the inverse Gaussian distribution. But the good news is most things in the world are simply wearing out, and hopefully the infant mortality portion of the distribution has been taken care of by burn-in or some other fashion. But in that case, you can see you have plenty of choices in the IFR case to work with, and there's a lot of software out there that will fit various distributions to data sets. The very last slide here in Chapter 4 is just a pointer that there are bivariate and multivariate lifetime distributions. There are about a half dozen exponential bivariate distributions, and I'm going to just quickly go through one such case. Let's say I need to get up early in the morning and catch a flight, and I decide I'm going to set 2 alarm clocks. And this first alarm clock fails overnight with parameter lambda 1. The second alarm clock fails with parameter lambda 2, and in both cases exponentially distributed. And finally, both of these are electric alarm clocks, so the utility company, if it goes out, then both of the alarm clocks will come down, and that's going to be exponential with a parameter lambda 1, 2. I'm calling these 3 random variables U1, U2, and U12. So there are really 2 ways that first alarm clock can fail. Either it can just break overnight, or we can lose power. And the minimum of those 2 is the lifetime of alarm clock 1. Likewise, alarm clock 2 can break all by itself overnight, or the utility company can go down, and that's considered T2. So when you're looking at bivariate distributions, you have something known as a joint survivor function, and that is S of T1, T2, and that is the probability T1 is greater than or equal to little t1, and, so this comma here is read as and, T2 is greater than or equal to T2. For this particular bivariate exponential distribution, that is given by this quantity right here for values of T1 and T2, which are non-negative. In addition to a joint survivor function, what is the probability that T1 equals T2? Well, that occurs when it's the utility company that goes down overnight, and that occurs with probability lambda 1, 2 over lambda 1 plus lambda 2 plus lambda 1, 2. The second is, what is the probability that alarm clock 1 fails after alarm clock 2? And that is this probability. And the probability that alarm clock 1 fails before alarm clock 2, and this is that quantity. Again, if you go out in the literature, you can find a lot of different bivariate exponential distributions. There is a multivariate exponential distribution, and so you will find some literature out there for multivariate lifetime distributions, even though in this class we're going to focus mainly on univariate exponential distributions. That completes Chapter 4, which is a survey of univariate lifetime distributions with an emphasis on the exponential, the Weibull, and the gamma. All of the other distributions are important, and you can unravel them in the same way we unraveled the exponential, Weibull, and gamma distributions.